Just to get an idea, is anybody using Elasticsearch here? That is way more than I was expecting. Okay. Interesting. If you have any in-depth questions, then just ask. Otherwise, I'll try to get started and start like at the beginning, like what is it and what is it doing, and we'll get into the more advanced topics as we go along. So everything is based on Apache Lucene. Sometimes I get the question like, what is the database behind it? And there is no database or any other data store behind it. It's Apache Lucene is the core library, and that is also what is writing the data out onto the disk. So there is no other database system. So there is Apache Lucene is its core library. It was started by Doug Cutting, looks like that. Anybody knows which other project he started? He started Apache Lucene and yes, Hadoop. Yes, exactly. He also started Apache Hadoop. So he started two very, very successful projects. And they're kind of related. Like in the beginning, the idea I think they had was like they want to do like a distributed Google as well and be able to do all of that. So they need stuff like storage and they need search. The Google part didn't really play out that way, but we still have the storage layer and data processing with Hadoop and search based on Lucene. And then Elasticsearch came along. It's not the first implementation built on Lucene. There are multiple other ones, but it's currently the most successful one, depending on which statistics you believe. But there are these DB engines database ranks, and it's by far the #1 search engine now. It was started by this mean-looking guy that is Shai. He started the project, and he's now the CEO of Elastic. I didn't know him for a long time, and when he started the project in like 2010 or something like that, at my previous company, we were always saying he's the search beast, because he's looking so mean, but also because he was producing so much code and work. Because in the beginning it was just him on his own, and I always imagine him sitting in his bedroom coding all day long and opening issues and closing issues and writing the documentation, doing everything by himself. But once you know him in person, he can also smile, and he's actually a very nice guy. So just his GitHub handle and Twitter handle, like his picture is very mean, and he looks very mean. So starting off, Elasticsearch and Lucene and everything is based on JSON. So we just take a JSON document and we want to store that and search it afterwards. We're not going into the actual search experience, like how do you search and why do you write queries. This is just about the distribution. So once you have a JSON document, our current version is 5.4, 3, probably tomorrow 5.5 will come out if we don't find any more bugs. And 6 is also on its way. So how do we get that into the data store? Other systems like Postgres, you have your binary protocol and you need your driver, but Elasticsearch is just based on HTTP. So what you normally do is you just run a curl command, or we also have lots of different drivers which basically abstract that, but it's all down there, it's just HTTP calls. So you do basically a post with a JSON document, and that's all you need. So you can just insert that. And then, since it's all JSON, you will get a proper response back. So since you just created a resource, let's assume there was no such document yet, you will get back a 201 internal node from HTTP, and it will just tell you, yes, I've created a resource, I've assigned that ID, and here's some meta information of what I've done in the background for you. And that is all you need. We also have Kibana, our visualization tool, that has kind of like a little nicer way to interact with that. The thing is called console, and you can see we do the same post command as in curl, but it's like we know the server name, and it's just like down to what actually it means. So that is kind of the same way to interact with that. We also provide you syntax highlighting and auto-completion there, so that is generally the way you want to interact with that. And then you will get kind of a similar response back, which looks something like this. It's pretty much the same response. So what you basically do is you have your client, and that does an HTTP call out to Elasticsearch, and it gives you back a 201, and that's pretty much all it does. So that's simple, right? So now we kind of want to take a look like what is going on in that box, because it's very easy to draw out that Elasticsearch box and say, well, that's all happening internally. Like, I don't really know what's going on and I don't care. Let's see how that is going on in the background and what it's actually doing here. So you normally you start a single node, whatever Elasticsearch version you have, you just do a bin Elasticsearch. It starts as a Java process, it will just run for you. And it will try to cluster with other nodes as you go along. So you start up a single node, it will become a so-called master node, so that keeps the state of that cluster, so that already one single node is a cluster. That's the smallest cluster you can get. So that one node you have just started, that is its own independent cluster, and it's just waiting for connections and waiting to do stuff for you. You can also add more nodes. In previous versions, these would always broadcast on the local subnet and listen for other nodes to join, which was very nice for the starting experience, but it's not really what you want in production. Like I can remember when I did, like a few years ago when I did training courses and I had a classroom full of people trying to do the training, all of those nodes then, like everybody would start up one node on their computer and they would form one big cluster. And then everybody would start influencing the data of everybody else. So if somebody inserted some data and somebody else deleted data, probably that other person deleted your data. And that's not really what you want. And kind of the worst case scenario is if you somehow connect from your local machine, where you have an Elasticsearch instance running, to your production system, like your VPN to your production systems or something like that, and you think you run a command against localhost, and then you do it against your production cluster. That's not really what you want. So kind of to fix these problems, we've changed our approach now, so it's not broadcasting anymore. By now you will need to explicitly configure all the nodes that should join one cluster. And then once you have told it, basically you will tell it like here is one other node or these other nodes, and as soon as they can see one or more other nodes, one node, they will try to form a cluster together. And here this has worked. You can see we have 3 nodes which form the cluster, like we have the one on the left hand side, we had that in the beginning. That's still the master node. And then we have these 2 other nodes, and you see all of them keep some data, and we'll kind of get into the data distribution a bit later. Third thing is there are different node types. So by default, a node does pretty much all the jobs you can give it. But you can also differentiate that, and they have also different roles. But it's all the same binary. You just run the same Elasticsearch node. You just specify in the configuration what kind of node type is that. So the first node that keeps the cluster state is the master eligible node. So by default, you would make for a production setup, you would have 3 master eligible nodes. So they can be elected master. Just a single one can be master at one time, but you can mark 3 of them to be master eligible, so they can be elected if others vote for them. That's kind of one of the first node types. The other one that you really need is the data node. The data node is that node that keeps all your data. That is the one that is actually doing your work. So that is storing the data and that is answering to your queries. You could split it up. By default, all nodes are master nodes and data nodes at the same time. But if you have a larger cluster with like 10 or more nodes, it might make sense to split up that workload and have dedicated master nodes and dedicated data nodes. Why? Data nodes do a lot of work, and they can get busy with queries and everything. But you want to have very stable master nodes because they keep track of your cluster state. And they should really be available, and they should not be stuck in some long garbage collection. Since it's Java, garbage collections can take some time, and then it appears like a node is not really there or working just because it's in the stop the world garbage collection, and you don't really want to be there. So the master nodes, they keep very little data. They just keep the state of the cluster, basically like what indexes or what data do you have, which other nodes are in my cluster, which aliases, which are kind of pointers, do I have. It's just like keeping track of the state of the system, but it's not doing any actual work. Whereas the other nodes, the data nodes, they are doing the actual work. And they will load a lot of data, and they will search, and they will have a lot of memory. They need to garbage collect at some point, and you probably want to split up those roles. That is kind of like an inherent Java problem, that garbage collections are a thing. So you can split them up, but by default, all of these nodes are the same. Then we have so-called client nodes. They're like smart load balancers. And you can tell, for example, your applications here, I have these 2 dedicated client nodes. They're not storing any data, they're just like connecting or receiving your requests, then going to all the other nodes in your cluster, getting their results back, combining them, and then handing out the final result. Why would you want to do that? Why are you not just doing that on a data node? So one of the reasons is if you have like very big aggregates, so you have lots of nodes which send you very big partial results, that one that one client node needs to combine all of these sub-results together. And that's a lot of memory to keep again. And the data nodes, they want to do it differently. Like they have data, they have stored that, and they want to cache as much from what they have stored on disk in memory, and they don't want to spend that memory for some aggregates or something like that. So you want to have your data nodes just serve data as quickly as possible, and you can use these client nodes then for big aggregates to collect everything in there. And of course they can load balance. So you can configure in your client application, you can configure multiple client nodes, and you will just know all the other nodes in the cluster, can connect to them, and get the data from them again. Another node type we have now is an ingest node. An ingest node is basically, when you get the JSON document, you could parse or enrich that. Parsing would be, since our stack is very common for log use cases, that you have a log line. And in that log line, let's assume it's, I don't know, an Apache or Nginx access log. And you have different feeds in there, but they're just one long string, and you will want to break out those different feeds. Like there is a return code in there, and there's how many bytes did you send back, and which URL did you hit. And the ingest node can parse all of these bits and pieces. It's pretty much like running a regular expression to split up the independent pieces. It can also do some enrichment. Enrichment sounds very weird, like what is enrichment? Enrichment would be you have an IP address and you want to get the geolocation of that IP address. So you have, I don't know, whatever IP address you have, and then you can just look that up in a GeoIP database and see, okay, that request is from St. Petersburg, and that is in Russia, and that is in Europe. And then you can store all of that, and afterwards you can very easily aggregate like how many people from Europe or from Russia or whatever have visited my site. That is an enrichment process, and the ingest node can do that as well. So you can have that part of your cluster too. Then there is, we've bought another company which did machine learning, though machine learning is a super overloaded term, so I'm always keen to point out, for us, machine learning right now means anomaly detection of time series data. So it basically learns what is normal in some interval, like you probably have some specific access patterns, and it will learn like what is expected and what is not expected. That is also an interesting process it needs to do. That is written in C++, so that we have another programming language in there, and you can run that on its own node, because you don't want to influence your searches. If you just do some big machine learning analysis process right now, you don't want that to impact your other nodes. So you would normally try to split out that machine learning node. And then finally, we had until now, we had so-called tribe nodes. They can connect to multiple clusters. So right now, one cluster needs to be in one geographic location. But we also have very big customers who want to have clusters in multiple regions. Like if you have these big gaming companies, they have players all around the world, and they want to store data locally to have quick queries and access times, but they want to have an aggregated view over all their clusters worldwide. And so the tribe node basically connects to all of these clusters and collects the data. And it sounds like a legend, but I've been told it's really true, that on one of the flights back from San Francisco to Amsterdam, the founder of Elasticsearch, Shai, implemented the initial tribe node code on that one flight. And the colleagues who were working with that still say, like, you can tell from the quality of the code. And so it was a quick fix, and it worked, but it was not that clever. Like, if you have 3 clusters and you connect to all of them, and each cluster has, like, assume 50 nodes, that tribe node will connect. That one tribe node will connect to all 150 nodes overall. And by default, Elasticsearch opens in every direction between every node connected to each other, will open 13 connections. So you have 150 nodes times 13 connections. That is a lot of connections to keep open for that poor tribe node. And so we have now added something else. It's called cross-cluster search. That is kind of the newer, more intelligent implementation, and going forward that should provide a saner and more performant approach. And I think in the next, not sure if it's the next major version already, but it will soon replace tribe node, and we will get rid of tribe node. Okay, so now we have all these node types running around there. Now we need to discover like how or where do we find all these nodes. So the protocol we have, kind of the starting mistake. You start off with the protocol, and then you're kind of stuck with it. So our protocol is called Zen Discovery. Zen, hopefully for peace and quiet. Not sure that always works, but we're trying to improve. Has been kind of a common question like, A, why have you started with your own protocol? That was kind of unfortunate. And B, why are you not replacing it with another protocol? So we have modeled it closer and closer to other well-known protocols, and we have now even written the theoretical proof of the correctness. It's just like a lot of work, and we have a few colleagues working on that protocol pretty much full-time, fixing all the bugs and edge cases. So what it does basically is consists of two things. By default, you're always using unicast. You have a list of seed nodes, like where do you connect when you start. And as soon as you reach one of these seed nodes, that seed node will tell you, oh, by the way, I know all these other nodes. And then you can find them and connect to all of them. And then everybody in the cluster is connected. The other thing that the protocol is doing is once you have discovered the node, you will ping the other node. So you can actually determine like, hey, that node is still available and up and running. And if a few pings time out or don't get a response, then you can assume, oh, that other node is dead now. So bad luck for that node, I'll find another one. Or the rest of the cluster will figure that out. And it's generally a peer-to-peer network. So every node in one cluster will open up 13 connections to every other node. So it's a lot of connections. But why do we have so many connections? Because for different purposes, there are different connections. So I think one connection, for example, is just for the pinging. And then there is connections for searching and for inserting, so you kind of have different lanes for different types of protocols and things you want to do. You always elect one master node. So if you start that one node, that is the first one in your cluster, that will see I'm the only one, so I'm the master node now. And as soon as you add another node to that cluster, it will see, oh, there is an existing master node. That is still the master node, I'll just join that one and I'll stick to that. And so you keep adding and adding and adding, and everybody accepts the same master node. In case that one master node dies, the other nodes will do a vote and elect another process or another node to be their master node. As I've already said, for production use cases, we strongly recommend 3 dedicated master nodes. A for maximum stability, and B, you should always have an odd number so that there is a good chance for having to find a dedicated master node through a majority. So the health check that does then is the master node pings all other nodes and checks are they available, and otherwise it will remove them from the cluster state. Since the master node, the main job of the master node is basically keeping the cluster state and seeing who is available, who is keeping what data, what is going on in my cluster. That is kind of the cluster state you want to keep track of. And you can do stuff like, what happens if there is no master node? What is your behavior? The default is I'm not doing writes. If there is no master node in my cluster, I'm not writing any data, but all the other nodes still know where the other nodes are, even without a master, and they can still read data from these other nodes. You're not writing anything new, but you can read by default. Though if you want to be more safe, you can even disable that, and you can say, I don't want, if there is no master node, like there is an ongoing election, which should just take like very short amount of time, like seconds. But still, during that time, I want all my queries to fail because I'm not sure in what state my cluster is. You can configure that. And kind of that is the most important setting. If you take away one thing from this talk, make it this. You should always have an odd number of master eligible nodes. And only if you have the majority, there you can vote for that master. So basically what you do is you have the number of master eligible nodes, which should be 3, and you divide them by, divide them by 2, and then you make sure you have the majority. So the majority of 3 nodes is 2. So as long as you have, of your 3 master eligible nodes, you have 2 that are available and can see each other, they can create a new master node. Why should we not have a lower number? Because assuming that you just have the minimum master nodes of 1, then you could have, with 3 nodes, you could have 2 nodes on one side and 1 node on the other side. And then kind of the network in between of them breaks. And then, since minimum master nodes is 1, that 1 node could think, well, I don't see the others, I'm the only one, I make myself master. And on the other side, you have 2 nodes and they only see each other and they think, well, the other one is gone, we'll make one of us master. Then you could have diverging states that nodes connecting to that side and to that side start writing data independently. And there's no good way to combine the data afterwards again. Like that is a totally manual process. There is no automatic combination of the data. So as soon as you have a cluster that breaks into two halves, and you don't have a single master node anymore, you will be in a very bad state. You could also select 5 master nodes, then the majority of 5 would be 3, then you can lose up to 2 master eligible nodes and your cluster is still up and running. Though for some people that is too much overhead, and normally we recommend having 3. Otherwise you will get into this split brain situation, and that will definitely kill your cluster. Like you will need to manually then select, like I have a split brain, like my cluster started to be 2 different clusters, and then you will basically need to say, I'm picking that one cluster, and all the other data that just went to the other side, I need to manually replay somehow or restore. There is no automatic way to restore that and combine that again. One very important setting is you can always check like in what state is my cluster in general. So normally green is everything is good, all the data is available, everything working as expected. Then you have yellow. By default, all the data in Elasticsearch, when you create one index, think of an index pretty much like a database in relational world. It's not quite the same, but it's kind of close enough. By default, we will shard every index into 5 pieces. And each one of these pieces has 1 replica. If you cannot allocate one of these replicas, your cluster will go into the yellow state. Like you still have all the data you want, so you can write all the data, you can read all the data, but you don't have the number of replicas that you have configured. You just cannot reach that for whatever reason. For example, if you just have a single node, we will not replicate on the same node, because there is really no point in replicating on the same node. Replicating on the same node, it would just duplicate the disk space, but you're not gaining any high availability. If the server process crashes, if the network is down to that node, if the power fails to that node, it's still gone. You're not gaining anything from replicating on the same node. So we will only replicate to other nodes. So if you start your little test cluster with a single node to do something, by default that will always be in the yellow state, because the default would be to have 1 replica. You cannot allocate that replica, thus your cluster will always be in the yellow state. With 1 node, that's okay. If you have multiple nodes, you will need to figure out like why is your cluster red? Why is your cluster yellow? Like why is it not replicating the way I want it to? And where you don't want to be is red. Red basically means one of the shards I have is not there at all. So I cannot read from it and I cannot write to it. I can read data from the other shards, but I have one piece of data that is generally missing in my system. That is, you don't want to be there. You can also do discovery of other systems, like you can do that by IP, which works on local networks normally. We also have integrations into cloud providers, so if you're on AWS, for example, it can figure out through security groups, it can figure out like, these are the other nodes that kind of are in the same security node, let's check if they have Elasticsearch running and try to make them join our cluster. So you can do stuff like that. So, we have built our cluster, which consists of 1 to n nodes, and now we want to start inserting documents. And I had index here, and index is unfortunately a very, very overloaded term. Like, if you're coming from the relational world, index is pretty much a B tree, I guess, right? Everybody thinks of a B tree, or like a regular index, or whatever you call it, for an index. Unfortunately, in Elasticsearch, indexes has multiple meanings. So the first one is toIndex is basically, we say toIndex is to store any data. Basically putting it into an index. Then Elasticsearch has a concept of an index. And Lucene, which also stores the data kind of on the layer below it, that also has a concept of an index. And depending on your context, the index or toIndex will be any of those 3. And generally, just because like, what is now Elasticsearch and Lucene? Like, how do they work together? Like, Lucene is the thing that stores data on disk and does the actual search, but that is only one shard, basically. Whereas Elasticsearch is doing the distribution, it's doing the replication, it provides the query DSL and the REST API. So when you use Elasticsearch, you're always talking to Elasticsearch, but down, like inside of Elasticsearch, what is actually storing the data is Lucene. So assume you have an Elasticsearch index, and that consists of 2 shards. I've configured it of 2 shards. So those 2 shards, each one of them is its own Lucene index. So you see, Elasticsearch index with 2 shards consists of 2 Lucene indexes. That is how they kind of work together. And if I have multiple nodes now, for example, if I have 2 nodes now, each node could get 1 shard or one of these Lucene indexes. And the Lucene indexes, they're not even aware of their situation. Like, they don't know that there are other Lucene indexes. If you do a search, like the search will basically come, you do the search against Elasticsearch, and it will then send the search to each one of these shards. Each shard is then responding with the data it has on its own, handing over the partial result to Elasticsearch, and Elasticsearch is combining that for you and giving you back the total result. But Lucene doesn't really know what is even going on. Like, as far as Lucene is concerned, it's its own Lucene index and it's the only one, and it's responding as if it was the only one. This is kind of the beauty that Lucene doesn't really need to know anything, it's just working along. So how do you store something? Right now, the unique combination is you have everything is stored in an index, which is kind of familiar to a database. Then we have a type. Don't think of type like table, because that is wrong and has caused a lot of confusion. Unfortunately, in the beginning we said that it's kind of similar to a table, and it is not. Like, you will be very confused. And we're getting rid of types in the next major version is kind of deprecated and disabled, and the version afterwards is really gone. So types is kind of an enumeration type of different data you put together. If you build anything right now, use a single type for each index. Don't use multiple types per index. It will be much easier to migrate in the future. And then there is a unique ID, and the combination of these 3 makes one document unique. And in the future, the type will just disappear, and the combination of index and ID is already unique. So what is the difference? If I do a post against that URL and a put against that one, this is the index, this is the type, this is the ID. So the ID can either be numeric or just a string, it doesn't really matter. Whereas in the top example where I do a post, there is no ID. I will need to generate an ID on my own. It's auto-generated, yeah, it's 20 characters URL safe, base64 encoded, it's globally unique identifier. It looks something like this. It's not very nice. But since the system is highly distributed and there is no single instance which can hand out your nice auto-incrementing or serial IDs, there is no way to work around that. So because it's a distributed system, it is generating IDs like that. And then we're doing consistent hashing of the ID. Why are we doing consistent hashing? Why are we not just storing the documents on the node where the key space is, basically? Why are we adding this overhead of hashing? Yeah, but I mean, you can still add nodes afterwards and just split one key space in the middle. That doesn't really make the difference, because it's just like the hashing is just a translation of Elasticsearch to something else that we like. In the previous example, we had Elasticsearch as an ID, and it's still like E still lands on that server, and you still need to cut that in the middle. But exactly. So thanks to hashing, you don't have any hotspots where you have more data. Since E in English is the most common letter, what is the most common letter in Russian? O. Okay. So in English and in German, the most common letter is E. So if you don't do the hashing, normally what you would assume is that if you just use strings, like you would have kind of a hotspot on E, and X or Q or something like that is very rare, and you would have very few documents. So you don't have an even distribution over your key space. And thanks to hashing, if you take the right hashing function, your key space will be very evenly distributed. You can influence that explicitly by having a specific routing information to keep data that is often related to each other on the same node, but by default it will be just the key will be taken, it will be hashed, and that will be evenly distributed over your key space. So we used DJB2 previously from DJ Bernstein, and it was super simple. Like, this was DJB, and he picked that magic number 33, and nobody really knew why. but that was the hashing function that we used previously, and now we've switched that. That's dead. Here's another one. Yeah, let's try another one. No? Ah, thank you. Let's see if that works. Yes, that's better, thank you. Now we switched the hashing to Murmur 3. If you really want to look up the code, is there. Murmur 3 is kind of a common implementation. Why did we switch? Because in the beginning we thought, well, DJB is perfect. We benchmarked it, like we created 100,000 auto-incrementing IDs. And it turned out if you have 3 shards, the distribution with DJB is pretty much perfect, whereas Murmur is a bit less evenly distributed. And with 5 shards, DJB is exactly perfect. Like you have all of them are the same, and Murmur 3 are not. But there are combinations where DJB really fails. Like if you for some reason picked 33 shards and somebody did, suddenly with DJB you have like lots of totally empty shards and the others take a lot of data. Whereas Murmur 3 doesn't have that problem. So I think before 2, if I remember correctly, it was DJB 2, and then somebody raised the issue that like the data was totally unevenly distributed, and that was not really the point of a hashing function. Like the point is to have an even distribution. And then we switched it over, and now it's consistently hashed again. And how do we distribute the data then? Whenever you create an index, you pick the number of shards, and you cannot change that number of shards later on. Especially you cannot split it up into smaller or into more shards. What you can do by now is you can combine 2 shards, but that is really only a factor. So if you have like 6 shards, you could shrink that down. The API is called shrink API to 3 shards or 1 shard afterwards. Because how are your documents distributed? You hash your document ID, you calculate it modulo the number of primary shards, and that is the shard number where your data ends up. And the master node then has a list of like, the shard 1 is on that node, and this is where to go. And that is kind of how this translation between ID and shard is, and how to look it up through the master node keeps the record of that. So if you want to write data now, you have your client, and the client connects to, the client doesn't know which shard is the right one, and it doesn't have to know. The client node just connects to any random node in the cluster. Any random node will do. And that node then knows which is the primary shard for that document. So that random node will either have, there will be an ID in there, so it knows how to calculate that, or it will generate the ID and then know it needs to go to that node. So that random node then knows, I need to forward that data to that primary shard. And then the primary shard knows, okay, I'm the primary shard, there is one replica configured, so I will replicate the data to that other replica node. And that is kind of the initial write process. And then you kind of want to acknowledge all of that, and this is exactly the way back. So the replica shard acknowledges back to the primary shard, then the primary shard says, yes, thank you, I've written it to myself and to you, very good. I will acknowledge it back to the random node that had the write, and that node will then acknowledge it back to the client. So those are kind of all the nodes that you need, or that need to come into play to write that data. We don't do locking or transactions in that regard. There is optimistic concurrency control, so every time you write a document, it will have, or it has a version field. And it starts at 1, and every time you update that document, that version will be incremented. And you can make sure, or you can say like, I only want to write that document if I have the latest or the current _ version of that field. Otherwise, I want to get an exception back. I will then try to fetch the data again and merge it together. So there is no transaction handling in that regard, but you can make sure through that version field that you only write the current version of the data. Something that can happen is if a node is flaky, or if you have like some bad garbage collection or something like that, how long a node should be like in a timeout state, and when should it be removed and kicked out of the cluster, and how long does it take until it can come back. So by default then is 1 minute, you can change that, and then you can say like, my network is a bit flaky, I want to give my nodes up to 3 minutes, only then they should be considered dead, and then I want to start syncing data again. Something that will make recoveries much easier is in the next major version number we have something called sequence numbers. So basically it's a snapshot version at some point, and you know everybody has written everything up until here, and then you can see, okay, the next batch of updates, have they been written out to all the nodes? And if not, you can just replicate those batches. Because right now, when a node just falls out for a few minutes of the cluster, it will need to replicate the entire state of the cluster, because normally it's not enough in sync that we can say, okay, this is exactly the same data, but you need to re-replicate all the data at once then. Because all the Lucene segments are written independently, and we can only do that based on the hash of the Lucene segment, and as soon as some write is slightly different, they will be considered different and you will need to re-replicate everything, but we will fix that soon.
Can you describe a little more details, like how do you do it with sequences? How do you do it with hashes?
So the sequence numbers is if I remember correctly, the primary shard will just generate the sequence numbers, and it's kind of like a known state at some point. And then, you know, all the other nodes have applied that known state, and you can keep track of these sequence numbers. And then when a node drops out, like say for 15 minutes, it comes back and say, hey, that is my sequence number. And the other nodes keep track of which sequence number do you have, like it's incrementing, since it's a sequence, it knows. And they know, okay, your state was up until here, you have the same state, and now I only need to send you these new versions which you have not seen yet. Yes, in 6 that will change. Like, we will get to the translog in a bit. The translog will be kept around for longer. Like, there is, I think the translog by default is kept for 12 hours or some certain amount of disk space there. So that data will be kept around for a longer time, so you can keep replicating that for a long time. And sequence numbers will also enable us to do cross data center replication in the future, which we cannot do right now. But thanks to these sequence numbers, you can then replicate that to remote nodes as well. So sequence numbers will both guarantees like how secure is your data, but also like feature-wise and recovery-wise, sequence numbers are a big deal, and they're one of the biggest changes in 6.0 for that regard. Okay, so how does Lucene actually store my data? Because right now it was all very high level and fuzzy. How does it look when Lucene is at work? So pretty much you have a buffer, and your writes get in there, and your buffer will get in there, and at some point you write out a new Lucene segment. Lucene segments are immutable, so as soon as you create that one, you cannot make any changes there. If you want to update a single field in a document in that segment, you will need to mark the entire document as deleted and need to rewrite it into a new segment. So the buffer is just buffering some data and then writing out the segment. By default, we will write a new segment every second if you have data in that second. You can change that. Generally, since you have a segment and you store that segment, a search needs to cover or go through all the segments and find the data that are in these segments. So there is a certain amount of overhead to every segment. So what you don't want to do is you don't want to create a new segment for every single write. Like you could force that, you could force a refresh of a segment, then you say, I want to create a segment now, but normally that's very bad performance-wise. And the other thing that we do is, because that segment here, that's not what I wanted. That segment that you are writing here, that can be in memory in the beginning. So in the beginning, this is in memory. And we have a translog. I think in Postgres is a write-ahead log. It's the same concept. You just keep all the changes you do here. They're kind of independent. Like you write out segments, they're in memory. You keep adding stuff to the translog. And at some point, that segment is f-synced, and then you can empty the translog, because then you know that has been written to this. But with the sequence numbers, to have all the changes for the sequence numbers, you will keep the data in the translog for a longer time. So that will change, that's right. And I've already said segments are immutable. Once you have written them, they are staying the same forever. You also have Tombstone files that mark documents as deleted in the old segments until they are garbage collected. So we have something called merge, which will combine smaller segments together, and in the process it will also remove new documents or documents that you have either deleted or that have been replaced by another update. And one of my ex-colleagues here has written a very nice visualization. It looks something like this. So you see these are the writes, and the gray area here, those are kind of the deleted documents, and you can see there are more and more deletes, and you write and stuff starts growing here, and then you kind of merge it together, and then the more documents you have in one segment. So you can see that the segments over time are growing, and when you delete data, the dark gray stuff, that is kind of the dead stuff that accumulates, and when you merge it is thrown out. It's pretty much like a garbage collection for that. And you can see how they grow over time larger and larger as you merge together new segments. That is the merging process. So, we've written data. How are we searching data? We have a coordinating node, and we have something called scatter gather. So what that looks like is you have that scatter phase. The client node connects, for example, to a dedicated client node, and we see we have some data here. A primary shard and a replica shard. Like we have written data to one index and it has two shards and one replica. So you see we have a primary shard P0 and its replica R0 is over there, and we have a primary shard P1 there and its replica over there. So if one of the node dies, the other one has still all the data, so that's kind of working the way we want. And if we search, we can either go to the primary shard or to any replica shard. It doesn't matter. First, for writing, you always go to the primary shard first, and then it's writing to the replica shard. But searching can go to either one of them. So that client node then says, okay, I want to read data from these two nodes, and it basically what it gets back in the first phase, whatever search phase it has, it basically gets. Assume you're searching for 10 terms that contain foobar. And then each single shard gives its 10 best results for foobar. And then that client node gets the list of those 10 results. It only gets the ID and kind of the quality, the score of those results. And then you do the fetch phase. Then the client node decides overall the top 10 results are these. Like you get a list of 10 each, because every node could have the 10 best results. So it's giving you the full list of its 10 best results if you want 10. And then the coordinating node just gets the 10 total best 10 best matches in total, and then says, and now I'm actually fetching these 10 documents. So in the next phase, in the fetching phase, it's going to the shards again and say, give me these specific documents now. And then it's getting back these documents, and then it's forwarding them to the client. And that is how you're searching in general. So you always have this scatter phase where you get like, these are the potential hits for the results you want to have, and they only contain the ID and the score. And in the second phase, you actually collect the right documents together and hand them over. Snapshotting. Since everything is written immutably, snapshots are very simple. You just copy the new segments that you have not seen before and copy them over, and that is how snapshotting works. So incremental snapshots are very simple based on that approach. So, stuff that could go wrong. We have a long list of stuff that can go wrong. One thing we have learned, we do have now, is we have a production phase and a development stage. So if you bind to any non-localhost interface, we assume you're in production. And we will not start up if you do any stupid configurations we know will cause you problems. So if you have not configured the right heap size, if you're using a JDK version that has not been released, if you have very few file descriptors, if you have very few threads configured, anything we know that will cause you pain in production, we simply will not start up, because it's better to fail early and take away some pain than to be broken afterwards. Stuff that can go wrong. Yeah, out-of-memory exceptions can always happen in garbage-collected languages. That's kind of a fact, unfortunately. We have some ongoing work that is mostly fixed. Every major version kind of fixes more things that we have. Like we have a very long list of stuff that can go wrong and that has been fixed and that will be fixed. Other things that are very bad, hardware as always, and the worst thing are normally users. Because people will just use your user abuse your system totally. Like we have that, and somebody complains on Twitter like, they're writing some stupid thing, and then you can see Shai with his mean picture. This time he's nice and he's reaching out like, can we help you in any way? And then a person is like, yeah, do you have Jira? And we're always like, yeah, we've been on GitHub like from day one, and that is kind of an insult to us already. And then after a lot of discussion, it turns out the user has just done some bad settings, and well, yeah, users are always the worst. Stuff we often get the question like, when will the next major version be released? This year. No guarantees, it's done when it's done, but it will be this year. Another common question is like, can I use it as my private data store? The first thing we always say, we're a bit careful around that. We always say like, yes, we know a lot of people who do. The more, or the better question would be, should you do that? And we're always there, it depends, like you don't have an SQL interface right now. We will have a read-only SQL interface in the future, but that's mostly for stuff like analytics. If you need transactions, it's also a bad choice. If you need something that scales very highly, that is a much better approach. But that is a very complicated discussion, like it will totally depend on your use case. Cross-data center replication will come later this year. Okay, to quickly finish off, yeah, don't forget, index is a super overloaded term. It's kind of to store data, Elasticsearch index, and to seeing index, and can be super confusing. We've seen how to store documents, where you go to the primary first and then the replicas. We've seen how we search, where we have this scatter-gather. So we first retrieve the potential results, and then we fetch the actual results. We've seen that there is documentation on resiliency. If you have any questions around resiliency, go to the documentation that normally has a lot of that stuff there. That's it. Any questions? And I always take a picture with you, so stay there. So I can prove to my colleagues that I've been working today. Otherwise, they're always assuming I have not been working. Smile, everybody. Very good. Any questions? Questions, anyone? Oh, by the way, we have lots of stickers over there. If you want to have stickers, grab stickers. Any questions now? If not, yes. Do we plan to get rid of Java? No. That will be very hard. Like since Lucene is already based on Java, that was kind of since this Lucene is based on Java, Elasticsearch has to be kind of based on Java as well. Though I think Java is also improving a lot. Like we have high hopes for performance on Java 9 and also memory usage. Is it just like generally against Java or garbage collected languages, or?
Garbage collected has been giving us a lot of issues, and not all people.
Yeah, sure. It's a trade-off with garbage collected languages, but no, I doubt that will happen anytime soon. On the other hand, Java has also improved a lot over time, I guess, and is always trying to improve. We will see how the new garbage collectors are doing. Like right now, we're still strongly recommending CMS, the concurrent mark sweep approach, and not G1 GC. Maybe that will change in Java 9. We're not sure yet. But yeah, garbage collections are always an issue. We're trying to get smarter around that. And there's also like more and more stuff we do off heap, so it's not everything on heap. That's normally why we recommend that you give 50% of the memory to the heap and 50% you just leave free, so it's file system level caching. That's.
Do you plan to use off heap memory for caching?
I mean, caching is done off heap already. That's memory mapped files pretty much. So the 50% you leave free is basically mapping of the stuff you have on disk into memory. And the heap mainly, we're also like with field values, we were using a lot of data for numeric values, but now we have doc values, and that has improved a lot because that is not in the heap anymore. So we are improving the heap usage, which also causes the long garbage collections afterwards. And never go above 30.5 gigs of heap, because otherwise Java will blow up your pointers, and then you suddenly have 64-bit pointers. And it will cost a lot of memory, but it will also cost a lot of CPU, so you should not do that. Normally, like the smaller the heap you can use, the better, because then the shorter your garbage collections will be. Yes?
Do you have plans to rewrite or stash file bits into something different different from JRuby or like Go or...
Okay, the question was about programming languages.
Yes, it's because of performance issues.
I mean, so yes, so Logstash started off as Ruby, is now JRuby for performance reasons. And yes, JRuby is also not that fast, but we are rewriting more and more parts of Logstash into plain Java. So we can, for Go we have the beats. The beats are written in Go, so they are native binaries. So you have file beat, packet beat, metric beat, heartbeat. They're written in Go. They're kind of the agents, forwarders, whatever you want to call them. They are Go. So we have kind of all the programming languages now. We have for machine learning, we have C++, for the beats Go. For Logstash we have JRuby, for Elasticsearch we have Java, for Kibana we have Node, Angular and React. For Curator to take care of your indexes we have Python. We don't have any production PHP code, I think. We do have a driver, but we don't have a production PHP application, if I remember correctly. Yeah, but no. So Logstash is getting more and more into plain Java for performance reasons, but it will still be Java or JVM based for a long time. So some of the, especially the encoding stuff, I think most of that has been rewritten to plain Java for performance reasons. And the beats are Go, so you don't need the JVM everywhere. So normally to collect everything, you just use the beats, so you don't need the JVM there. But that's the plan. Well?
What is your adventure with unit tests and passing just tests?
Yeah, so passing is always relative. One of the bugs I have mentioned that was found by him that was mostly fixed. We do invest a lot of effort into that, and also proving like the distribution part. I don't think we can officially claim we have passed anything yet. And here also, like once we release 6, maybe he's doing another test on that. On the other hand, we always have to say like we are not claiming we're a database. We're always saying we're a data store, whatever that means. And also the other thing that is kind of like people, if you use a database, you expect you store something and you get it back immediately. Whereas for the search, since we have the segments, we have this refresh of 1 second by default. So if you store something, retrieval by ID is immediate, but searching has kind of this delay, and that is kind of by design. So all of these tests, I'm never sure like how much they apply, but there are some anomalies that can occur, and we're trying to get rid of them one step at a time. So sequence numbers are kind of the first step into that direction. And resiliency is generally a very strong topic. We're learning, like we have been too lenient in the past. We're getting better now, everywhere, hopefully. Okay, thanks a lot.